In our next section, we're going to look at Rapid Spanning Tree Protocol and talk about some of the differences between it and legacy PVST. We'll talk about some of the changes behind the scenes of how RSTP works in terms of convergence, and then look briefly at some of the configuration options. Now, Rapid Spanning Tree was originally defined in 802.1W, but it's now part of the main standard, which is 802.1D as in David. Main changes, as I had mentioned before, is that the reconvergence is no longer timer-based; it is synchronization-based. So previously with legacy spanning tree, you have a failure of the link. You wait until the maximum age expires, then you wait for the listening and learning delay before you actually go into the forwarding state. So worst case scenario, it's going to take about 50 seconds for reconvergence to occur. In the case of rapid spanning tree, assuming that the network physically is designed correctly, like not in a ring, then typically it's going to take less than 1 second for convergence to occur. We'll also see there are some changes in the port states and the port roles, but the path calculation stays the same. Path calculation meaning how is the root bridge elected, how is the root port elected, how is the designated port elected. So like I mentioned, that book, The Cisco LAN Switching, even though it doesn't talk about rapid spanning tree, it's still good for the details about where is the root bridge placed, how does the topology calculate. What is really changing here is just the reconvergence, the amount of time it takes in order to figure out there was a change in the topology and to fix that. Now, as we compare it to the legacy spanning tree states, we had 5 states of disabled, blocking, listening, learning, and then forwarding, where typically we would start at the disabled state where the port is down. We would then transition to listening. We would transition then to learning, then ultimately to forwarding. This would take 15 seconds in order to go to listening, 15 seconds to go through learning, and then ultimately once you're done forwarding, it should be about 30 seconds total. If you're coming from the blocking state, it might be a little bit longer. Like I mentioned, there's an additional timer that is the maximum age. Depends how long it takes for you to figure out that the other neighbor is gone. Could take up to 20 seconds. Then you go from blocking to listening, learning, forwarding, so about 50. In the case of rapid spanning tree, though, we simplify this just to 3: discarding, learning, and forwarding. So discarding then is basically the equivalent of disabled and blocking, which means that we're dropping frames, dropping them either because the port's down or dropping them because the port is blocked. End result is still the same. We're not forwarding any traffic. Listening and learning are combined into simply the learning stage. So it's effectively the same. It's just that we're trying to build the CAM table. So we're learning about where MAC addresses are located, putting them into the MAC address table, but we're not actually forwarding traffic towards those destinations. So we're listening for broadcasts, flooding them on, and then based on that, we figure out host A is located that way, host B is located that way. Once we finally go into the forwarding state, then we can actually send the traffic. Okay, also we have some changes in the port roles. So we're now decoupling the port roles from the port states, where the root port and the designated port are the same as before. Root port is going to be the one that is facing upstream towards the root bridge. So we have the root bridge at the top of the tray. We have switch 1 downstream. Its root port faces northbound towards the root, and then the designated ports are facing southbound away from the root bridge. But we have 3 additional port roles, which are alternate, backup, and edge. Edge, as we talked about before, is the equivalent of a port fast port. The backup port is going to be the equivalent of the uplink fast behavior, which it's going to be that is the other way around. It is the alternate port is the equivalent of uplink fast. Okay, edge is the equivalent again of port fast. So alternate is going to be an upstream facing interface is going towards the root bridge, but you're not currently using it. That is in the blocking state. Okay, the backup port is kind of a corner case situation. It's not really seen in that many cases. But alternate is going to be one of your primary ways to do rapid reconvergence. So this is going to allow you to do the equivalent of uplink fast. Your directly connected root port goes down. You do a handshake with the switch on the other end of the alternate port. Assuming that we agree upon where is the new root bridge placed, what is the path cost end to end, then this normally takes less than 1 second, and then you can go right into the forwarding state. Okay, so the alternate port is in the discarding state. Basically, it's dropping traffic. It's a blocked port. The backup port is a backup designated port, which is kind of a strange situation. Normally, you only have this when you're connected downstream to a shared segment, like you're connected to a hub or some sort of other layer 1 repeater, but you have multiple links facing downstream towards that segment. But in most cases, in real design, you don't normally have this. You typically have point-to-point links between the switches that are full duplex, so you would not typically have the use case for a backup port. But backup port, the basic logic is that it's going to activate if the designated port fails. So like an alternate port, it's operating in the discarding state. It's a blocking interface, but it's a backup downstream facing port as opposed to an alternate upstream facing port. So alternate goes up, it's a backup for the root. The backup port is the downstream port, it's a backup for your designated port. Okay, then as I mentioned previously, the edge ports, these are the equivalent of port fast. So your interface comes out of discarding, so the physical link status comes up, layer 1 comes up, you immediately transition into forwarding. Okay, the other big thing for this is that you don't generate a topology change notification when the interface goes up or down, and you do not need to do the synchronization on a edge port, okay, which we'll talk about in a second here, what specifically that means. But from a configuration point of view, it's the same command as saying spanning tree port fast. It's just the behavior is a little bit different when you are running in rapid spanning tree as opposed to running in a legacy spanning tree. So as we talked about in the previous section, port fast you can configure multiple ways. You can go directly to the link level and configure it, or you could do it under global. End result is the same. You're just turning it on the interface, either globally or at the interface. And then in the case of rapid spanning tree, the port is going to run as an edge port, which changes what happens in the synchronization process. Okay, we also have a couple different link types. This says maintains edge status as long as no BPDUs are received. So this we'll come back to in a second. This is actually the same behavior as I mentioned in port fast, is that if you configure an edge port between two switches, it automatically figures that out. It's not going to cause a loop in the network. As soon as the BPDU comes in, it knows to revert it out of edge state and go to normal point-to-point state. Okay, so besides the port types and the port roles, we also have link types. Link types are either point-to-point or shared, basically meaning full duplex or half duplex. Normally, the interfaces are going to be point-to-point by default, unless for some reason you're going to some sort of layer 1 repeating segment or like a legacy hub. Okay, not that you normally would, but is possible in some certain designs. In that case, you would want to set the port manually to be spanning tree link type is shared, which affects the synchronization process. Basically, the reconvergence is not rapid on shared segments, only rapid convergence on point-to-point segments and on point-to-point edge ports. But from the CLI, you can see that this normally is the case, that when you look at the show spanning tree, so here we have show spanning tree VLAN 1, it says the link type is point-to-point. Unless it says SHR, then it's not a problem. Okay, so normally point-to-point is the default. Okay, only point-to-point designated ports use the sync process for rapid convergence. So again, this means that if there's a failure and you need to reconverge, on shared interfaces, you go back to legacy listening and learning delay rules. So it would take 30 seconds to transition a shared alternate port or a shared backup port into either the root status, so from alternate to root, or from backup to designated. Whereas with the point-to-point interfaces, those can just do the handshake, the synchronization, and then you can immediately transition to forwarding. Okay, so how does it do that specifically? This is called the synchronization process. The goal of the synchronization process is to figure out what is our root port. So in previous legacy spanning tree, you figured that out just by sitting there and waiting for 30 seconds, waiting for the BPDUs to come in everywhere. You figure out whichever one has the lowest cost of the root bridge. Then eventually you go into the forwarding state. Okay, difference now is that rapid spanning tree is an active protocol. You basically have the equivalent of like an adjacency between the switches, where they say, hey, I want the root bridge to be X. Do you agree? Yes or no? And then once we agree, then we can go to forwarding state. Now, what happens is that when the switch initially boots up and starts running this spanning tree process, it's going to elect itself as the root bridge. So it elects itself as the root, and it's going to send out all of the designated ports. Hey, I'm the root. Do you guys agree with this, yes or no? Now, assuming that it is not the root bridge, okay, so let's say that we have a case where switch 1 is at the top of the tree, and we have set its priority to be 0. Okay, so we know that this guy 100% of the time is going to be the root bridge, assuming that no one else has their priority set to 0. We now plug a new switch in. We plug switch 2 in, we power it up. It comes on with a default priority of 32,768. It says, okay, I'm the root bridge. I'm setting all of my ports to be designated ports. Because the root bridge, from the root bridge perspective, every interface is facing away from itself. It's facing downstream or southbound. So on these designated ports, we send out the synchronization request. Switch 2 says to switch 1, hey, I'm the root bridge. Do you agree? Switch 1 says, no, I don't agree. My priority is 0. I'm the root bridge. Switch 2 says, okay, that's fine. That's not a designated port. That's really my root port. And now I can continue the synchronization process downstream. So essentially, synchronization starts at the top of the tree at the root and then moves downstream towards the leaves. And assuming that the network is not configured in a physical ring, then convergence should be rapid. There were a couple questions about this earlier about recommended resources for more details about the reconvergence process and other things about rapid spanning tree. We do have a bunch of detailed write-ups on our blog about this. So if you search for understanding rapid spanning tree, it is this one here, understanding RSTP and STP convergence. And there's a bunch of details here about what specifically happens when you have a direct link failure versus an indirect failure, and what are the potential convergence cases that you can run into, like how long is it going to take for the network to figure that out. And one of the ones that is kind of interesting here is rapid spanning tree in a ring topology. And there's a case that you could run into which is called count to infinity. This is basically what your distance vector protocols were trying to avoid by doing a maximum hop count. Like RIP has a maximum hop count of 16. It makes sure that if the update goes out and for some reason keeps going around and around and around all the way around the network and comes back, as long as it hits 16 hops, we're going to expire the update and it's not going to go up to infinite. But in the case of rapid spanning tree, it actually is subject to these type of failures. But it would have to be a very specific failure in a ring topology that would cause this problem to happen. It's basically like the root bridge was at the top. It failed. I go to send the sync this way, and the synchronization requests run into each other, and then one of them gets canceled out, and it keeps going around and around and around. So there is a fix for this, is basically not to run spanning tree. There's a separate protocol that you would run in this type of environment, which is called Resilient Ethernet Protocol, or REP. Now, I don't think that REP is within our particular scope. It would be something that's in the scope of like the service provider exam, but the specific use case for this is in Metro Ethernet rings. So point being is that rapid spanning tree does get sub-second convergence as long as the physical network is correct. But if you have some sort of like maybe industrial network that you need to physically wire it as a ring because of some sort of distance limitations, you don't want to use rapid spanning tree. It can have cases where it takes like 5 minutes for the network to converge, or potentially never converge. You have to power cycle the box in order to fix the problem. Okay, so again, the way that it does that is by sending the request out the designated ports, asking the box on the other end, do you agree on who is the root bridge? Okay, that whatever the box is on the other end is going to look at this info. If they do not have a better path to the root, they say, okay, I agree that my path to you is now going to be the root port, and I'm going to continue the synchronization process downstream. Okay, so let's think of this from our traditional like access distribution core design. If you have layer 2 switching 3 levels deep, where we're assuming like your core network is going to be your layer 3 edge. Okay, so we have the core, and let's assume that we have core switch 1 and core switch 2 because we want some physical redundancy. So we're going to say one of these guys is going to be the root and one of these guys is going to be the secondary. Okay, then we have these triangle connections that are going down to like distribution switch 1. another one that's going down to distribution switch 2, and then we finally go down to the access layer. Okay, for simplicity, let's say we just have access switch 1. Okay, theoretically, all 5 of these switches power on at exactly the same time. They all elect themselves as the root bridge. Okay, they all start sending out all of these interfaces saying, I'm running, or sending the synchronization request out to everybody. Hey, I am the root bridge. Okay, when the actual root switch, let's say it's the one on the upper left that we configured this guy as priority 0, as soon as distribution switch 1 realizes this, it says, okay, I'm no longer the root. This becomes my root port. These other interfaces are facing away from the root port. These are potentially my designated ports. I'm going to send them into the blocking state, but at the same time, I'm going to continue to send the synchronization down. So I send the synchronization down to access switch 1. Access switch 1 says, okay, that's a better cost to the root. This now becomes my root port. This other one is potentially a designated port. I continue to send the synchronization that way. At the same time, though, core switch 1 sent the synchronization request this direction and this direction, which caused distribution switch 2 to elect that as the root port and core switch 2 to elect that as the root, which means that they're now forwarding the synchronization requests back and forth to each other. These ones, effectively, they realize that, hey, that's not part of the topology that we want to be switching over. Those are the interfaces that go into the blocking state. So assuming that you don't have some sort of connection where like the access layer is plugged back into the core, this is where Rapid Spanning Tree has a problem. That you send the synchronization request down, and then it comes back up, and then it goes down this way and comes back up. Normally you don't want the network to be physically looped like that outside like your Metro Ethernet ring type designs. So in most typical cases, as long as the layer 2 network is only maybe 2 hops or 3 hops deep, then Rapid Spanning Tree convergence is going to be less than 1 second. Okay, so again, once the box downstream receives that and it agrees on the information, it's going to unblock the port. Okay, if the information downstream is not accepted, if I get better information, then we're going to update the root port. So again, that's the case that I power up, I elect myself as root, I tell you, hey, I'm the root bridge, and you say, no, you're not. My priority is better than yours, so then I swap my roles. So I move my interface towards you to be root, my other interfaces become designated, and then I synchronize your information back to the boxes behind me. Okay, the end result somehow is that everybody is going to agree upon this. Okay, the port blocking, the goal of this is to prevent what's called a transient loop. Transient loops are subject in link state protocols like OSPF or ISIS are subject to these temporary or transient loops. That means that when I'm in the process of converging, your information is different than mine temporarily before I send you my new information. And I could send a packet to you that you're pointing directly back to me, and then we start to bounce the packet back and forth. Now, from a layer 3 routing point of view, that's not as big of a deal as it is in layer 2, because layer 3 routing has a time to live header that's included in layer 3. So either the IPv4 packet or IPv6 packet, if I bounce it back and forth 255 times, eventually the packet's going to get discarded. But in the case of layer 2 bridging, since Ethernet does not have a TTL, transient loops can be very, very disruptive to layer 2, or potentially be 100% disruptive, like the CPU goes to 100% and then you can't switch any traffic at all. So this is the reason behind the scenes why it blocks the interface while it's in the process of synchronizing. So it is a disruptive change when you have to switch the root bridge, but since the process is less than 1 second, usually it's not that big of a deal. Okay, so synchronization, the whole goal of this is just to make sure that everyone agrees on the same root bridge.